Understanding tasks and stack memory is fundamental to grasping how operating systems manage running programs. A task is essentially a program that's currently executing on your computer. The operating system manages these tasks to make efficient use of the CPU, especially when multiple programs are running simultaneously. Each task represents an active program that needs processing time. Tasks can be classified into two main types. CPU-bound tasks require intensive processing power and spend most of their time using the CPU. I/O-bound tasks spend more time waiting for input and output operations, using the CPU in shorter bursts. Stack memory is a crucial area where temporary data, function call information, and local variables are stored while a program is running. It operates on a last-in, first-out principle. This diagram shows how stack memory works with function calls. Each function call creates a new frame on the stack, containing local variables and parameters. The stack grows and shrinks as functions are called and return. When a task's time slice ends, the operating system performs a context switch. The current task's context, including data in CPU registers, is stored in the stack. This allows the task to resume seamlessly when it gets CPU time again. This context switching mechanism enables multitasking, allowing multiple programs to share the CPU efficiently while maintaining their individual states. This diagram illustrates the complete task management flow in an operating system. Tasks move through different queues and states, from the job queue to the ready queue, then to CPU execution, and potentially back to waiting states or termination. Understanding these fundamentals of tasks and stack memory is essential for comprehending how modern operating systems achieve efficient multitasking and resource management. Round-robin scheduling is one of the most fundamental and widely used CPU scheduling algorithms in operating systems. It provides a fair and simple way to manage multiple tasks competing for processor time. Round-robin is a preemptive scheduling algorithm, meaning it can interrupt running tasks. It ensures fairness by giving each task an equal opportunity to execute, and it's simple to understand and implement. Tasks are organized in a ready queue that follows the first-in, first-out principle. New tasks join at the rear of the queue, while the scheduler selects tasks from the front for execution. The key concept in round-robin is the time quantum or time slice. This is a fixed amount of time that each task is allowed to run before being preempted. Let's see how this works in practice. Here's how the round-robin algorithm works step by step. A process is selected from the ready queue and begins execution. If the process completes within its time quantum, it terminates normally. However, if the process doesn't finish within the allocated time, it gets preempted and returns to the back of the ready queue. One important consideration with round-robin scheduling is context switching overhead. Each time we switch from one task to another, the system must save the current task's state and load the next task's state. This process takes time and can impact overall system performance, especially with very small time quanta. Round-robin scheduling has several important advantages. It provides fair CPU time distribution among all tasks, prevents any single task from monopolizing the processor, and works well in time-sharing systems where responsiveness is important. However, round-robin also has some disadvantages. The frequent context switching creates overhead that can reduce overall system performance. It may not be optimal for CPU-intensive tasks, and choosing the right time quantum size is critical for good performance. In round-robin scheduling, processes transition between different states. New processes enter the ready queue, get selected for execution in the running state, and may either complete, require input-output operations, or get preempted back to the ready queue. Modern operating systems have evolved round-robin scheduling in several ways. Priority-based round-robin combines fairness with task importance. Adaptive algorithms dynamically adjust time quantum sizes based on task behavior. In cloud computing, round-robin helps distribute workloads evenly across multiple servers for better resource utilization. Round-robin scheduling remains one of the most important and widely used scheduling algorithms due to its fairness, simplicity, and effectiveness in time-sharing systems. While it has some overhead costs, its benefits make it a cornerstone of modern operating system design.